Let's Boltzmann Q&A. What is a tensor product lattice? So we start introducing lattice Boltzmann usually with a discrete velocity set in one direction, so one dimensional, and we say there can be velocities in positive direction and in negative direction and one non-moving velocity. And these are velocities along one cardinal direction, say x, and this can of course also be in y or in z. So there is supposed to be a set here. Now, in order to derive a lattice for two-dimensional velocity set, we have a tensor product lattice in 2 dimensions. And what a tensor product simply does, it takes one of these velocity sets in one dimension, say here, and puts in each of the velocity, in each of the 3 velocities, it puts the same velocity set in the opposite, in the orthogonal direction. So here, here, and here. So then starting from 3 velocities in one direction, for example, in the x direction with the index I, we get now in 2 dimensions, we get 9 velocities because we have 3 times 3 of these velocities. So this is pretty simple what is a tensor product lattice in 2D, and now you can easily think about what is a tensor product in 3 dimensions. This is taking another one-dimensional D1Q3 lattice and putting 1D2Q27 lattice in each of these points. And now what comes out looks a little bit crazy. Now we have 3 indices, I, J, and K, and each of this index and can either take 1, 0, or -1, where I remind you that we write the -1 on top. This is a Miller indice. Okay, so what does this lead to? This leads, of course, to a set of moments for this 3-dimensional lattice. And here we have, of course, when we have 27 velocities, we have also 27 independent moments. And of course, some of these moments now are of higher order. So the good thing with tensor product lattices is that it is pretty simple to see what moments are actually coming out of this, because we now have the moments with 3 indices, of course, and each of this in each direction, because we had 3 velocities, we have also 3 different moments. And what you see here is that each index of the moment goes from 0, 1, and 2, and we have all permutations of this. So, and now, as I just said, this of course means that some of these moments are of higher order. So if you have all moments with all permutations in 2, for example, that one down here, then you see that this is a 6th order moment. However, all the moments that are above the 3rd order, which are indicated by this coloring here, they are considered ghost moments. And so they are actually not really required for solving the Navier-Stokes equation. So even though they take up some space in memory, we don't really need them. So, and this leads us to a further point. not all lattices are tensor product lattices, but we can also prune the lattice. Prune the lattice means we are cutting out specific velocities in order to get rid of these ghost moments, which we do not need for the lattice, for solving the Navier-Stokes equation, but we have to do this in a way to keep the symmetry of the lattice. Now, the way this is done is by distinguishing between different energy shells. An energy shell is all the velocities that an energy shell is composed of all the velocities which have the same energy, where we define the energy by the square of the indices of the lattices. And you see the D3Q27 lattice has 4 different energy shells. So the particle that is not moving at all is one energy shell. All the particles that are moving in the cardinal directions, they give us one energy shell. And here we have 6 of them. Then we have the energy shell of the particles moving in diagonal directions. So this would be in the lattice, this would be the edges. There we have 12. And then we also have the 3-dimensional diagonals. This would be the corners on the lattice. And of these we have 8. So now in pruning, what we are doing is we are taking out specific energy shells and generate new lattices. So for example, if we just take the energy shell 0, 1, and 2, what we end up is the D3Q19 lattice, which is one of the more popular lattices. Then if we take the energy shell 0, 1, and 3, so this would be the point in the center, the faces of the lattice and the corners of the lattice. Then we come to the D3Q15 lattice. And if we just take energy shell 0, so the non-moving particle, and the edges, then we come to the D3Q13 lattice, which is one that is not so popular. So what this does to the moments is usually not so easy to calculate. The only lattice for which this is very obvious is the D3Q19 lattice, where we can now look at the dropout moments. So these moments here are the moments that are kept in the lattice, in the D3Q19 lattice. So there is, of course, all the moments that we need and on top of this, some of the ghost moments, so 3rd order moments and 4th order moments. And here we have some dropout moments that would be present in the tensor scalar tensor product lattice, but they are not present in the D3Q19 pruned lattice, which are here the some further 4th order moments, 5th order moments, and here 1/3 order moment and the 6th order moment. So this leaves us with the explanation what is a tensor product lattice and how can we reduce the tensor product lattice to other lattices that do not include too many ghost moments. Thank you for listening.